Hi. So the voice is right. Good. All right. Thanks a lot for having me. Let me do a little bit of warm-up questions so that I know my audience, and then I'll speak. So, how many of you have, by the raise of hand, how many of you have used GPUs in your work? Quite a bit. Nice. And how many of you have done high-performance computing specifically targeted for GPUs as well? All right. Thank you. And how many of you have cloud computing and MPI-based distributed memory computing? Oh, good. Thanks a lot. Thank you. So, I work at Forschungszentrum Jülich. It's a big research center in Jülich, somewhere here. And we have around 7,000 employees. And there I work in Jülich Supercomputing Center. We do supercomputing operations, operating the supercomputer. We have application support, so if you have applications which want to go on supercomputers or GPUs. And then domain science support, so we also do some research there. And we have training and courses on GPUs and hackathons and programming in general. And software engineering as well, to maintain the quality of software. And in that specifically, I work in GPUs and other accelerators, so FPGAs, IPUs. I work in this lab accelerating devices, and there we consult softwares and we help them with optimization. We are associated with also with NVIDIA Application Lab since 2012, and with RISC-V development programs nowadays, and also Jupyter Early Access, which I'll talk about in a minute. So I thought what to talk about, and I realized that a lot of people know C++, so programming in C++ would be like a short talk in general, but what is important is when you program on GPUs or supercomputing, then you have different kind of constraints. And I thought I would introduce that. And the way this talk came about was Miro told me that maybe you should present something about the supercomputer that you're having. And so we have this, we are going to have soonish this supercomputer called Jupyter. It has two parts. The first is Jupyter Booster, which is actually the Exascale supercomputer, which has 4 Hopper GPUs, the GH200, of which H100 is the more popular model right now. And then we will have a cluster which is for the RIA one, which is a ARM CPU, and so this would be a supercomputer. And then these are some of the technical details, but the important details is that it will have around 1 exaflop of compute, and then it will be operating with 17 megawatts of energy in general. And this is kind of the site of the supercomputing center. So the person there standing is my boss, Andreas, and you can see the first scale, and this is it being assembled. So when you develop a supercomputer, you don't just put it together and expect it to run. You need the applications to be ready for your new supercomputer. And for this, we have two systems, Jedi and Jetty, which we are trying to help our applications so that they can run on them, so that when the final supercomputer comes, they are ready and the supercomputer runs from the starting. And this is coincidentally also my work currently, where I am participating in Europe, where I am helping applications with optimizations and also mostly with continuous benchmarking. And so just a moment, and then my background is in computational fluid dynamics, which is where the motivation comes from. And this is kind of a fluid which is moving through the space, and then I'm trying to simulate it by moving the mesh which is simulating the fluid along with it. So this is kind of my background. And then the question is, what is supercomputing in general? And what is supercomputing in general? So you mostly program on GPUs currently. In the old days, you would do CPUs. And I thought first I would start with a simple C++ program, which I can explain, and then we'll get into the details of why we want to do all of these things here. So when you want to program a GPU, you have this main function. So you have the host memory, you are initializing it somehow. Then you allocate memory on the GPU, you copy the host memory to the GPU memory, you run some function on the GPU, and then you get back the results by copying back the memory from the GPU to the host, and then you print the results. But then you see there are a lot of different things going on here, like this global annotation, or this thread index, or this chevron signs, as we call it, the triple thing. And what is this going on, and why is this important, right? So to give context of why supercomputing and why GPUs, I am going to explain a little bit about the problems we solve. So this is kind of a Laplace equation in a way, with the load factor here, and this you can think of it as something that simulates the diffusion of gases through systems. And the way we want to solve it is we compute the solution at different time steps. So we start from n equal to 0, which is the 0th time step, and then we go forward, and then this is the formula we use. This formula is not that important. The important part is that if we want to compute the solution here, we are taking the data from the top cell, the bottom cell, the right and left, and then combining it together as well. And this kind of data dependence is important. So this is kind of the code, and it's much more details, but what is important is that you iterate over all the cells and you compute this formula over and over again, and then you go. And when you do this, you are simulating this over really large systems. So this matrix of cells that I showed, that can be billions of cells, and this can go to hundreds of terabytes of memory. And what you want to do is you want to scale this, you want to make the system perform very well on big supercomputers. And what this means is you want to be able to, so on the right you see what is called a scaling diagram. So this is the runtime of a given problem on, let's say, 8 nodes of a supercomputer, and then as you increase the number of nodes you are allocating, the number of machines you are allocating to the same problem, you see the problem size go down, and it goes down approximately as linear. So if you have 8 and if you have 16, then for 16 it should be ideally 2 times faster, so half. So this is one part. So if you have a bigger system, you can solve a same problem much faster. So that is called strong scaling. But then if you have a bigger problem, then you want to solve, if you have a 16 times larger problem, and if you go to 16 times larger computer, then you want to be able to solve that problem in the same time. And this is called weak scaling. And here you can see this problem is actually not weak scaling very well, because otherwise all these things would be in the straight line. And so these are the two challenges that we have. So the thing is, why do we need really big supercomputers for this? Why am I talking about more machines? And so the reason is like this. When you have if you have a small matrix here, small number of cells, then all of them can fit in one computer's memory. And for a long time, actually, this was the case. And you can see here the Cray supercomputer in the right from 1989. And this was kind of in the same architecture, because what it had was it had a central memory, and then all the CPUs would access it, the central memory. So the memory was kind of coherent, and then you would access all this data in the same node all at the same time. And so all the CPUs are seeing the same memory space and all the same. But this cannot last. As you know, nowadays, even when we have chiplets instead of a chip, even then the latency is big enough that cached coherency can introduce slowdowns. And so this is not possible today. And yet, if you see the last some years of supercomputing, you see that the power of supercomputer has gone up. And how is this, the performance? and it is from what we call distributed memory. So we take this big matrix, we divide it into small matrix, and we give each of them to each machine, and then we make them communicate. So what happens here is each of the machines runs a process, runs the same process, but they are now all of them are having their own memory spaces, different memory spaces. And then the only way they can communicate is through messages, of course. And this is how they communicate, and then they solve this problem. Now, when you look at it, you realize that there are two things which can affect the performance of this kind of a system. The first is how much can you process in one single block, and the second is then how much time does it take actually to communicate. And if you can process a lot of things in a single block, then even if your communication takes a long time, then you are fine because you are still bottlenecked by the compute. But if your communication is the bottleneck, then you cannot do much, because communications, especially if you see here, communications can be a lot, and this can lead to bad performance. And so this is where actually GPUs came in, because for a long time there were CPUs in supercomputers, and CPUs, as you can see even today, they can process a certain number of operations per second, and the trade-off between communication and compute was not high. So GPUs, as we'll see, there is still a trade-off in GPUs, but GPUs promise us to increase the number of computation we can do in a single node here. And this means that even if the communication is a little tight, then a little bit slow, then we can still do compute without losing performance. And this is where actually the supercomputers are different from other setups, like, let's say, for example, cloud computing, because the communication is much faster, it's time sensitive, so you can actually do this communication every second, or maybe even every half a second or something like this. And for this, this is kind of a network topology of the Jewel's booster machine that we have. So here you see there are, the orange are the machines, and then they are connected in this configuration which is known as full fat tree, because all nodes are kind of connected to all other nodes. And when you have your systems in networks like this, then you get nice performance. But then this is for as you can see, there are only 48 systems here, and then this group of 48 systems are then connected in more complicated setups. So this is why we want to do supercomputing. We want to solve really big problems. We cannot solve them on small computers, so we divide them into a bunch of small computers. We make them communicate. And then the question is what to do about the part here. And so then we come to this. So this is a matrix. We want to ensure that this part is the biggest, and then the rest parts are used for communication, and they are small. And this is where GPUs come into play. So just a moment. Yeah. This is where GPUs come into play, because what they do is they do a little bit of a trade-off. In CPUs, you have this arithmetic logic units, and you have the cache and control, and each ALU kind of has its own, sometimes has its own decoder or not, but mostly they are very fat units in a way. And what GPU does is it removes a lot of intelligence or a lot of logic from ALUs and makes them very lightweight, and then the control is from the other parts. Yeah. So the GPUs are generally connected as a PCIe card. In supercomputers, they are also connected with another interface which is much faster. Here it is 64, and then I'll show later. Nowadays, this can go up to 900 Gbps per second. And what you do is then you prepare your computations on the CPU, you send them to GPU, you make the GPU do the computations, and you get it back. Another feature of the GPUs, especially the ones which we use for supercomputing, is that they have this really high bandwidth memory, which has this bandwidth of 3.3 terabytes per second. And this really helps with large data processing and large data movement. So this is kind of the core of how the GPU works. The logic in each unit for a combined logic, and I'll show that later. And then it has this really high bandwidth memory to feed all the logic processors. So A100 in the past had bandwidth of 1.5, and then H100 and new it has 3.3. So some more details about how this architecture is processed. So here you see one single node of a supercomputer, and it has this 4, let's say, processors in 4 sockets. These are ARM processors, Grace processors, and they have 72 cores each. And then there are 4 GPUs in the between. And then each GPU is connected to a dedicated CPU. And then the GPUs themselves are connected by, you don't see it here, but they are connected by this NVLink, which is 2 into 150 gigabytes per second network link. And then the GPU and the cores are connected by 2 into 450 gigabytes. 2 is bidirectional, so 450 gigabytes in each direction of network. Then the GPU has a 96 GB of HBM memory, and this LPDDR memory is 128 Gbps. So, and this whole node is connected to the network using 4 InfiniBand chips. Each of them are around 200 gigabytes per second, which is 100 gigabytes in each direction. So, yeah. So then to the GPU and the CPU. So we have the CPU here, we have the CPU memory, and we have the GPU here. So for the GPU, as I said, there's a trade-off in the logic. So you have a scheduler which schedules all. So the way the GPU works is it takes a lot of data and it processes it in parallel in terms of threads. And so it has a lot of threads. But then there's a scheduler which kind of schedules multiple threads at once. And so this is how the logic part is reduced, and this is how the performance can be kind of increased in the same silicon. Yeah. And so to study a little bit of how this performance works, we need to look at the thread details. So I think a lot of people are aware about this kind of threads. So you have single instruction, single data, which is kind of a single thread program. You have multiple instruction, single data, where you have multiple threads running. Then you have to worry about data synchronization and all of this. And then you have SIMD, which is single instruction, multiple data, where you have one single instruction which processes 8 or 256 or 512 bytes at once. And what GPU does is it kind of takes this idea and a little bit and then changes it slightly. So instead of having the exact same operation run on all the data, it divides the data into small parts, which let's call them warps, and then inside each warp it does what essentially happens here, where it runs the same instructions in the warps. And so what it means is, and this is called single instruction multiple threads. So you are running multiple threads, but all of these threads are kind of lightweight threads on the GPU, and they can process all the data in lockstep. generally this warps, they are 32 threads at once. So this is the size of the block. And so by dividing it into this kind of a configuration, you can reduce the amount of scheduling you want to do and improve the performance. Yeah. And this is, yeah. So a CPU core can be thought of as one scheduler in the GPU, and then which is called a SM, and then it operates on 32 threads at once. And then I'll show you in a moment, using a large register file, it can swap between different threads by quickly switching the registers. Yeah, and so this is how the GPU kind of looks. You have this big L2 cache here, you have the HBM memory connectors here, and then you have all these green things are the SM blocks, which is one scheduler. And if you zoom into one of them, you see this. So you see here the L1 instruction cache, the L0 instruction cache, the L1 instruction cache, and the scheduler and the register file, and these are the actual cores, FP64 cores, FP32 cores, INT32 cores, and then the tensor cores, which are pretty new. And you can see that, and you can see the register file here, which is 16,000, so around 16 MB, 16 mega into 32-bit. So these are the number of registers that you have. So these are quite a large number of registers, and that's why you can swap the data quickly, and that's why you can run the threads quicker as well. And this is where actually the first idea comes of why we want to program GPUs in a different way. Because if you think about this, now let's look at this program. So let's first look at the program on the right. You have a structure which is a point 3D, which has float x, y, z, and then you have a function, and this function is reading this value x. So now remember that since we are running a lot of threads, this operation is happening in parallel for a lot of point 3D structures. And so when we do it here, we see that there are all these FP64 modules, and all of them are going to execute this instruction. But for this, they have to load this data. And as you can see, the data loading is not that powerful, because again, data loading is communication, data loading is instructions, and you can only give so many instructions to the CPU at a time. And so what happens is, when you load this struct, due to the cache line effects, everything here is getting loaded. So even if you want to load in this FP64 only one integer, it is loading all of these 3 points. And generally, all of this kind of communication, computation, what happens is, you will load, you will have this expression, and then you will have another expression, maybe points I dot y, or point, maybe line I dot y, some another. And so to load two values here, points I dot x and line I dot y, you have loaded 6 integers. And this is where the crux of GPU computing comes from, because this is now wasting bandwidth, memory bandwidth, and because you are loading 6 when you only need 2. And since you are bounded by memory in general here, you will suffer from performance. And so this is the first thing this is the first indication that you need to do something differently. So what people do is, instead of having an array of points, they will have a structure of arrays. And so what happens here is, when you are loading x.i, the things which are getting loaded in the cache line are x.j, x.k, x.l, and these are what you need. And this is what will give you the bandwidth, and this is what will give you the performance. So this is kind of the first thing that you see. And out of everything that I've shown with the communication, when you are programming on GPUs, this is kind of the most important thing that you need to remember. With CPUs, you have really low latency. You have a CPU core, you have all these operations, the processing is there, the data loading is there, the waiting, but for GPUs, they are high throughput devices. They are not not low latency devices. They achieve performance by throughput. And what they do is, when they are waiting for data loading, if you can feed your GPU with another data that can be processed in the same time, then the greens will occupy 100% of the GPU, even though the threads themselves are not really performant. And so if out of everything that you want to take, this is an AI generated image, out of everything you want to take, if you want to take one thing out of GPU programming, it is that you must find a way to keep your GPU well fed with data. That's the only thing. And then everything else will follow. Sorry, just a moment. Yes. So then, once you know this, then we go to programming supercomputers in C++. And there are a lot of things that you can do. So there are Vulkan, there is OpenCL. We generally, at least myself generally, we know about this. So I'm going to talk about mostly this. So when you do programming on GPUs, there are different models. And the first model that is there is native, which is CUDA or HIP. And this is the model that the vendors provide. Then there are other models called directive-based parallelism, which I'll come to in a moment. There is standard parallelism, which can be provided by PSTL or STUDPAR. And then there's standard-like parallelism, which is provided by libraries like Cocos and Executors. So what we'll do is we will go over them one by one. So first we revisit the Jacobian solver. So this was the solver. And this is the data transfer, so data dependence between this. And so first let's try to do the native code. So before doing the native code, we have the what is the thing about native. So native platforms are the platforms which are directly supported as the primary interface for computing, I would say. And what they do is they provide fine-grained control, because all the features generally appear here first. They generally have first-class access to debugging and profiling, but then they are platform-specific. And so for AMD, you have HIP, for NVIDIA, you have CUDA, and for Intel, you have OneAPIs and SYCL nowadays. So let's go back to this function. So what is happening here? As I told you before, the host is being initialized, which means I'm also allocating it. Then I allocate arrays on the device. I copy the data from host to device, and then I run this code Jacobi. So what is this doing? What I am telling this code is run one block of n into n threads and run this function for that. So what it will do is, for each thread it will run this function. And what you see is, because I have chosen this quite nicely, n into n square, what you see is that you can get the thread index from here, and then you can do some arithmetic to make the single dimensional thread index into multi-dimensional, and then you can use that index to your matrices and do this. So each thread of the GPU will execute this instruction. And then, so each thread will execute this instruction, and as you can see, for computing one value, I am using 1, 2, 3, 4, 5 values. So you can say that for, and how many operations are there? There are, let's say, 1, 2, 3, 4, and 5 floating point operations. So you are doing 5 floating point operations on 5 values. So, sorry. So when you do 5 floating, so this is called arithmetic intensity. it's almost one operation per byte. And this is how you measure your performance, characterize your code for performance. So if you have one floating point operation per byte, that means that the number of computations you do is directly dependent on the bandwidth you have. And this goes back to the first point I had, where if you keep your GPU well fed, then you can do this computation. If your GPU is not well fed, then you cannot do one operation every byte, because you are always waiting for the bytes to come. And the way to characterize this often is in this roofline model. What this roofline model shows is that this line here represents the bandwidth of the GPU. So the compute performance, which is determined by the bandwidth. So if you have less amount of data, and you can use the complete bandwidth, then you will be somewhere on this line. At some point, you are, and on the x-axis is the operational intensity or the arithmetic intensity. So for me, I was on 1 flops per byte. So if I go straight, the maximum performance I can achieve would be somewhere here. If someone has, and this is the maximum compute that the GPU can do. And this depends on the tensor cores that it has, or tensor core or the floating point cores. And so if you are doing 32 floating point operations per byte, then you should be able to get this performance. And so this is how you can verify whether the performance you are getting from your code is correct or not. So when you write this code, then you, depending on your data structures and what you optimize, you check whether where your application is on this, whether it's here, whether it's here. Ideally, it should be on either this line or this line, because this operational intensity is dependent on the algorithm of your code. It does not depend on the implementation, but then where you are on this line will depend on the implementation. And this is what you can do, this is what you can do with the profiling. So, and then you can do a profiling of your code. And when this is one of the profiles that you can do with your code. And when you do the profiles, if you see here, you can see a figure called theoretical occupancy, which is 25%, which means that this code, depending on how many registers it is using and how much data it is using, the profiler has determined that it can only use 25% of the total performance. And so if you want to improve, then you should improve these things and things like this. So this is for the CUDA code, but the CUDA or the HIP code, but that's not the only option. There are other options as well. Maybe I'll just skip this in a moment here. And this is the directive-based parallelism. So CUDA is one way. So in CUDA, what you did is you wrote these functions, called this CUDA, malloc, CUDA, memcopy, and you called the exact kernel you want to execute on the GPU. But on directive-based parallelism, what you can do is you have kind of this code, and it is a serial code, and then you can introduce this directives in your code, and then this code the compiler will parallelize your code for you and put it on the GPU. So what is happening here is, for example, this was this code and this was a parallel for loop, and then if you use a directive-based parallelism, then this becomes into a pragma ACC. So I am using an OpenACC code here, so pragma ACC parallel loop. Sometimes you want to do reduction. So for example, this is a reduce operation here, error is fmaxr, and then you need to specify reduce as a special variable in this directive and stuff like this. So this is the directive-based parallelism, and if you want to have a mental model of it, then it is a fork join model. You have your code, and then there are parallel things in your code, and then you put them in OpenMP directives or OpenACC. And these are slightly different. OpenMP, the master thread is a part, here it's not a part, and so on. Yeah, so this would be the parallelization workflow. Then there is standard parallelism. This is another way you can program your CPUs. This is exactly as you would do with today's parallelism, but on CPUs. You can do on GPUs as well. You have this transform function, standard algorithm, begin, end, begin, see, the funcject or functor or function object, all the names that you have here. And then you provide this executor. But you now need to use compilers which support this. And so for NVIDIA, you have NVC++ and the stdpar library. For AMD, you have HIP stdpar with HIP C++. And with Intel, you have 1DPL with DPC++. And this is what, So this is what you can use today. It's not from what it is still in works, so it's not fully complete. But when it is complete, you would be able to use your standard C++ code with your standard GPUs. There is a caveat though here, because all of them currently, as I know, at least most of them, they use unified memory. And what unified memories means is that you don't specify whether your memory is on GPU or CPU, and the compiler automatically or the runtime automatically decides when to copy memory from GPU to CPU. So if you have one operation on the CPU and one on GPU, continuously copying data between the two, and this can lead to reduction in performance. So you have to be careful about that. And currently there are no function pointers, at least in NVIDIA, so you cannot pass a function pointer here. You have to pass a function object, and this function object correctly, even though some of it is automatic. Maybe last, So then, because of the standard parallelism, when you use standard algorithms, the things are very in a way kind of rigid, because you can only use the algorithms that there are. You can only use the models that we have in C++. So some people are, let's say, not completely happy with it, even though they are mostly happy with it, I would say. And so there are these libraries called Cocos, and there's another library called Raja. And what they do is their aim is to have a single source implementation for C++, which means that they have a single C++ implementation, and it runs on all the different GPUs, it runs on all the different CPUs, and all of this. It is a descriptive programming model. I'll come to that in a minute. And it aligns with C++ on parallel STL. So if you write parallel STL, then it will look like parallel STL when you do it. But the difference here is that because of the way they have structured their abstractions, they can implement architecture-specific optimizations for each different architecture or each different GPU. And the way it looks is like this. So for Cocos, they have there are a lot of different things in Cocos, but the two core concepts I would say is that they have something called Cocos View, which is, let's say, the standard multidimensional array form that you want, and then they have functions like this, parallel for or transform where. You can give a name to that function, and then you can give an execution policy, and then you can give the function object. And what it does is essentially depending on which function execution policy you have. If you have an integer policy, then it will run this function object on 0 to n threads, so n threads total. If you have a MD range policy, then it will run on a multi-dimensional range, so it will have a two-dimensional CPU threads and all of this. And then the view is like the multi-dimensional array, and so this would be a double array of 3 dimensions, and all the 3 dimensions, the size of the 3 dimensions is known at a static time. at compile time, and then here you have one which is runtime dimension and the other 2 dimensions are compile time. So you have these views, you have these things, functions, and then when you combine them, you can run the programs, and it ensures that there is no spurious memory copy. It ensures that the programs are always running on the correct backend, and it ensures that the way these policies are designed, it ensures that you are not overdoing any calculation and you are using the optimizations. And then it has some, for scientific people, it has specific features like advanced views, which are if you want a column measure layout or if you want a row measure layout, then you can choose them, and the performance, it changes a little bit, but you can still try the same. And then finally the executors, which are something new in C++. And currently I know about 2 libraries which have implemented executors for GPUs. One is NVExec from NVIDIA, one is Pika from CSCS. And what you can do is you can have structured concurrency in a way. And so here you can see you have a thrust device vector, which is an NVIDIA library, and then you get a raw pointer from that, and you have this function which returns positive if it's on the GPU, otherwise it returns 0. You create an NVIDIA execution context, and you execute it. And this is currently still in infancy, so we'll see how it goes. Yeah. So final thing, I've talked quite a bit about some things here. The final thing I would say is I have talked a lot about GPUs. I've talked some about the programming models, and you need to, often the decision is how you want to select the programming models. And I would say there are 5 things which are important for selecting the programming models. One is the vendor support, because the vendor should be dedicated, because otherwise you will miss out on the optimizations, you will miss out on the features that you can run. Then performance and portability, and this is kind of important because, as you saw, if you write a code in one language and then you are restricted to one vendor of GPUs, or if you're restricted to something, then it might be something that you want, but if you don't want it, then you have to think about portability, and then you have to think about things like COCOs, things like standard parallelism, stuff like this. Explicitity and redesign. So standard parallelism, as I said, you cannot really do, for example, control the memory because it's controlled internally. You cannot. So oftentimes it's good, but sometimes you might want to do more. And this is where explicitity comes into play. Then toolable code. So if I go back to my OpenACC code here, for example, you can still tool it, but there are this kind of executors, for example. This is much more toolable because you can overload this stream with your own stream, and then you can put logging into it, you can do stuff into it and stuff like this. And instrumentable code is generally not a problem, but you should still be aware of it, because a lot of things that you do will come from profiling, and which I was showing here, which will come from profiling. So every time, because the GPU is a complex beast, a lot of things can be non-intuitive, and so profiling is very important. And if you have a code which cannot be profiled very well, or where you cannot see how all the kernels are acting very well, then you won't be able to optimize it as much. And finally, this is a slide about, so we, in Accelerating Devices blog, we maintain a table about what programming platforms there are for GPUs and which GPUs they currently support. So green are fully supported, and then yellow are not that well supported, and then there are other complicated things. And if you want, you can visit this and know more about the support. So thank you for your attention. I hope I have given at least an overview of what it takes to program in GPU and what models you can use. And I would like to credit all the people in my group who made most of the slides here. Thanks.
Thank you very much. Great stuff. I learned some things today. So do you have any questions for Jayesh?
I have a question mainly regarding slide 14.
Slide, sorry?
14.
1-4?
1-4, yes. It's mainly regarding functionality. So since you have a lot of resources on supercomputers, how do you know when to stop if the convergence doesn't give you a good solution?
How do you know when to stop when the convergence?
Yes, because you have a lot of resources and you can go into an infinite loop, for example. How do you know when to stop when the convergence function doesn't give you a proper result? It doesn't converge to a proper result.
Just a moment. So you mean the size of the problems, like when to stop?
Yes,
the size of the problems. All right. This is fortunately or unfortunately, the more you increase the size of the problems, the more your communication will increase at some point, and or you will run into memory bandwidth limits. So memory capacity limits of GPUs, or you will run into communication problems. So this is out of your hands in some ways, but I think unless you have something really non-linear going on in your simulation, if you have a proven stability for then you can actually go as large as you want if the hardware allows it. But if the hardware doesn't allow it, then you have to look at what point does the communication become dominant, what point does the you're running out of GPU memory, or what point, something like this.
Thanks.
Yeah, after all these amazing technical details, I wonder more than ever how this big supercomputer is actually used. I suppose a majority of users just runs existing optimized programs, fluid dynamics, whatever. But then imagine there is a scientist who has a very specific code for a specific scientific problem, and now he would like to run it on a bigger scale on your supercomputer. I assume you just will not admit a code to the supercomputer that is not well optimized, which then opens kind of a hen and egg problem, right? How do you optimize when you are not allowed to use the machine? And is there any chance that a normal scientific software developer can make a code ready for the supercomputer within a couple of months, or should he rather hire a specialist who will work on that for 2 years?
Yes, just a moment. So, I forgot Roland did give me Wi-Fi access, but I forgot to enable it. Okay, but I'll just let you know anyway. So, there are different ways to do this. All supercomputing centers in Germany, at least, they give access under different rules, and there are 3 kinds of supercomputing access you can get. The first is a test access, where you show that your code has some potential, but this is very easy in the sense that if you have a CPU code, then if you show that you have some performance, if you have good performance, then you get this access. Then there's a development access where you get compute time on the supercomputer for 2 years, for example, and then you are expected to improve your code, the performance for 2 years. And then there's a third access, which is the benchmark access, or let's say the large scale access, where you are doing large scale computations with the optimized code. This is the logistic part. Then the scientific part, and there are two options, three options again. The first option is when you apply for this compute time, there's an option that you ask for resources of technical expertise as well, and then you can get this access. The second is you can write a proposal with someone. You can write a proposal with a scientific proposal with the supercomputing center, and this allows you. The third is you can actually pay for supercomputing time. Even on our supercomputers, industries can pay for supercomputing time. And then actually the fourth way is you can attend hackathons, which are GPU hackathons, which are specially organized by Open Hackathons Foundation. And here people like me, we go as mentors, and we do a lot of stuff. We take some applications which are not on GPUs, put them on GPUs, or if they're already on GPUs, then we optimize them. And once we have this collaboration, then we can start collaborating on it again in future as well. So essentially the answer is that you need technical expertise, but the ways to get it can be different. You can also hire people separately, but yeah.
How about you were talking about profiling on GPUs. What about functional correctness and debuggability? So what if I have an algorithm which I made a matrix multiplication and it delivers me 5 answers correctly on CPU, and I just annotate it to a CUDA use case and it delivers a different answer? What options I have, how I tackle such a problems?
Yes. So debugging on GPU is generally a little bit harder, much harder. Also for the debugging, you need support from the GPU sometimes in the hardware. So for example, if you have NVIDIA GPUs, they have a tool called Compute Sanitizer, and this would at least figure out most of the sanitization things that you would figure out in CPU. So if you have out of memory access, or if you have, so there's limited support like this. But apart from this, it's difficult, I would say. And the strategy then we generally suggest is, instead of trying to port codes on the GPU, you should generalize your code and then switch the executor. So for example, if you have a transform function and you have written it manually, put it into transform function and switch the executor. So because then your executor, you can also debug the same thing on CPU and you will get the same errors. And yeah. Does that answer your question?
Yeah, thank you.
Okay. Hi. Thanks for the talk. That was great. I have a question. So what you just described, I understand that applies to programming models you described. That applies for programming one cluster, one node, right? What programming models do you have for distribution, or is it somehow transparently included in these programming models?
No, it's not transparent. The way this runs is, let's say you have this on the right side, you have 9 nodes and you are communicating between, you have running simulation on all of them. So generally what you would do is, you would take there are 2 important softwares that are required, the scheduler, and one is called an MPI message passing interface. daemon, or so the scheduler will take one binary and execute it on all the different systems. So you have 9 processes now running on your system, and but then you run it with the message passing interface daemon enabled. So you run the executable through your message passing interface daemon. So use message passing as a launcher, and then what happens is that each process, it knows that it's a part of a bigger thing of 9 process, and it knows what its rank is, like what its index is in that big. So each process now knows that it is a part of a bigger ensemble, and then it knows that what its rank is. And now with this logic, you can do everything else that you want of communication and everything.
But you have to do, which programming model do you use for that? I mean, do you have to?
It's C++. It's okay. Sorry, I understand now. It's a C library, let's say. Yeah.
I guess I get it. So, but you have to. Do you have to partition your problem in advance in a suitable way?
In a way, yeah. So let me quickly find out a program which. Yeah. So.
I get it.
So what's happening here? This is the mpi.h API that you are including. So first you initialize. This is how you know that you are inside, and this is the size of your things, and then this is the rank or the index, and then what you can do is you can, so then you also you can do stuff like, let me see if you can do stuff like if rank is 0, then read the file and then put the file into array, and then for each rank you communicate part of that array to that rank, and then you start running the program on each rank. So this is how you would do it. So you manually partition it and then you do it.
I get it. And another follow-up question. So when you're programming for your specific supercomputer, right? So does it differ in too many ways from working, for example, of GPU cluster on which you buy on Azure or AWS? Do you have to consider something specific?
Yes. So there are two things which are important here. So the first thing I was describing is that the communication right here. When we have this kind of a network, then the communication is guaranteed. So in Azure, if you have a cloud and you are not doing geolocation or you are not doing some co-location of the clusters, then your things can be on different networks, and you are or it is the same network but they can be far away, and then the communication increases. Also, you will use TCP in your networks there. Here so that is another error, because TCP is robust against different things, so it has more overhead, all of this. And so the main thing is communication is much faster, and so all these problems which require a lot of communication, you can do much better on supercomputers than.
So, but assuming, just doing the devil's advocate here, I want to build my own supercomputer on Azure. Assuming I set up a shared memory configuration with all the InfiniBand nicety that I can do, like eliminating all the issues you mentioned, like latency, networking, and stuff. Do I have a chance to achieve something like, of course not on that scale, because I don't want to build my own compute center, but like a fraction of the capacity of your supercomputer, which kind of scales with cost? Is it possible in theory?
Yes, in principle it is. Most of the hardware that we use is you can buy off the market yourself. That's not the issue. There are small, so let's say you can achieve 85% performance, 80% on your own. Then what happens is that then you really get into the details, and this is very difficult to optimize. For example, sometimes you need to select the correct number of message passing bus. Sometimes for example here, this problem, the domains which are close enough are also close in communication. So a certain type of, like, it really doesn't matter which network you have maybe sometimes, because as long as you place the nodes together, you are fine. But if you have something like fast Fourier transforms where you can have global communication between different parts of, then the network suddenly becomes important. And this is a full fat-free network, and then this is a dragonfly network, which is different, but then the network position really becomes important, and so then it becomes a trade-off, which kind of applications you are running on your system and what network you want. Yeah.
Thank you very much. So
There's
I
a question.
have another question, but if I don't want to take too much time.
No.
A point that I think you left off is to these questions about these distributed environments is that actually in normal praxis people don't write all their kernels. In fact, they'll use many, for example, on the CUDA platform, they'll use, for example, cuBLASM. And cuBLASM Parallel has this. There are lots of these parallel libraries that are already there. And then they will use them. Typically, actually, an environment is there. People are, don't write terribly much CUDA. They'll probably use OpenACC. And the big advantage of OpenACC, which you have to actually know a bit of CUDA to write good OpenACC, if not, your OpenACC code will be shit, because it can target different accelerators, but depending upon the accelerator you have, your OpenACC code will be very different, as you tried to show, for example, the difference performance between SOA, your structure environment. These have very, very different performance depending upon whether or not they're going, for example, to threads on CPUs versus GPUs. And for scientific computing, it needs to also be mentioned that Fortran is supported by OpenACC.
Yeah, that's a good point.
And Fortran's alive and well.
Yes, that's a very good point. That's why in this graph, we have, can I go to the end directly? The F is for Fortran here. Yes. Fortran is supported. So what, sorry? Sorry? NVIDIA has CUDA, NVIDIA calls it CUDA Fortran. It's Fortran version. So you can write, for example, you can do concurrent in your code, and then it will execute on the GPU with, NVIDIA calls it CUDA Fortran, that's why we put it here, but yeah, it's all right. So that's a good point, and then it all comes back to the support of performance and portability. Even though technically, for example, OpenACC looks portable, it might not be portable in the sense that you might not get the same. Sometimes you might even have to change the directives, but you might not get the same performance, or you might not get the same optimizations on different GPUs, even if you write the same code, even if there is nothing architecture specific here. Is that what your point was in a way?
Yeah, I mean, depending on, because the whole point of OpenACC is you can specify and target different accelerators. I mean, if you use the OpenACC implementation of NVIDIA, it's typically, for Tesla.
Yeah.
Basically, for NVIDIA GPUs, but Clock, for example, is the more general OpenACC implementation, which can target anything. And also within the OpenACC, you can also target cores. Cores called FPGAs. There are lots of backends, for example.
Yeah.
Years ago, you even had, NCL backends.
Yeah. True. Yeah.
Hey.
Hi.
Very simple question. From your own experience, what do you find the most unsatisfying, bothering, and annoying about the current state of the available paradigms and tools for GPU programming?
What do I find? So could you please repeat the question?
What annoys you the most about the available programming paradigms and tools that are available for GPUs?
So this is a very personal annoyance. I wouldn't qualify this as a engineering knowledge. I really love nice abstracted code, let's say. Why am I doing GPUs is a different question. But whenever you want to do GPUs,
You really shouldn't in that case.
For me, the most annoying thing is, like, this is, I think everyone has to accept this, but this is really the most annoying. That is well, you can still abstract this, but yeah, your performance and your abstraction will conflict multiple times, and finding the correct abstraction so that you can run on multiple architectures without and this is where my software engineering desires also come, because I want to be able to have a sustainable code which I can maintain and everything, but still have the performance, and this is a difficult problem. I don't know, and this annoys me, and this is what keeps me working, I guess, towards this.
Thanks.
Hello. Hello.
There is a question there at the end.
Yes, here.
Yes.
Hello, Fayon. Thank you for the talk. Coincidentally, at work, I have to look into the single node GPU dispatch for an internal development. So I actually have a question about parallel framework here. You mentioned that each vendor has their framework, but of all of them, only NVIDIA dispatch to NVIDIA GPUs. HEAP can dispatch to NVIDIA GPUs and AMD, and SYCL is an open standard that can dispatch to all three of them. Is there still a reason to be in the walled garden of NVIDIA? Did you do a comparison of all of them on your hardware to see there's still like a strong benefit to use the CUDA ecosystem? That's like first part of the question. The second part is since SYCL, or perhaps I can let you answer first this one, and I have a follow-up question on that.
Sorry, I did not understand the second. Sorry.
So did you do a comparison of HEAP, SYCL, and CUDA on your ecosystem, on your hardware, because they can dispatch HEAP can dispatch to GPU, and SYCL can also dispatch to NVIDIA GPUs.
Yeah. So I think so let me answer it part by part, maybe. So there are applications which are doing the same code on multiple GPUs, but the performance comparison is a very hard task, let's say. We are never sure whether we can compare the platform, whether we can compare the GPUs, or whether we can compare the code. And let me give you a reason for this. For example, you see here the register file has a certain size, the number of x64 has a certain size, and then there are loading units which you don't see here. And depending on how many loading units you have, depending on how many registers you have, the sweet spot of performance, the sweet spot on reaching the top of this line, can actually be little bit different algorithm on different on architectures. So first you have different algorithms themselves. Then once you have different algorithms, then you have to worry about whether you are actually be able to faithfully implement that algorithms in C++, because of various reasons, object model or whatever. And then you have to worry about whether whether the compiler is optimizing them currently. And it's a difficult problem. Like you cannot say that one GPU or one platform is definitely supported on another. We do try that, but it's very difficult to make these comparisons. What we think is better, and this is what generally happens. For example, when we are doing this new supercomputer, purchasing this new supercomputer, we have this we published this paper, and then what we did is we took all the applications that we have, we thought we liked, in the sense that we have running on the supercomputers, which we already, and then we benchmarked them, and then we decided what to do about them. So when you want to compare this, you really have to compare with your applications that you're going to run. and then you really have to test for your applications, you test for your platform, and then you have to find a perfect fit. You cannot. It's very difficult to give a general statement.
Yes, I understand that for specific hardware you need different potentially. So would you recommend if you have NVIDIA GPUs to only use CUDA? If you have like AMD GPUs to only use like HIP? Because theoretically you can compile, you can develop with the HIP language and be able to generate code for NVIDIA GPUs. That's what you can do. You can, in SQL, can generate code for all vendors, hardware vendors. So in terms of portability, in general, you would like to have more portability. This is what Cocos propose as well, right? So what would be then the comparison between SQL, which is also an open standard with like several implementation, which has the same level of API or paradigm level as Cocos? Like, is there still a need for Cocos in the future, for example, with SQL existing?
Oh, okay. Like this. I don't know the future, I would say. But it's always good to have a vendor independent effort going on, because it can also push things in different directions, I think. Yeah, I would say it is still a nice thing to have, because Cocos is not exactly like, there are multiple things that they do. It's not just portability, right? And they have, for example, the view class. It is ref counted, so you don't accidentally delete it. They have a lot of different wrappers for BLAS routines and all of this. So, and then they have all these executors which people would have to write by hand otherwise. So I think there is a lot of value anyway, even if they only write C++ and do no specific thing. I think there's still a lot of value.
Okay, thank you.
Anyone else?
I have another small question here. Jayesh. On one of the first slides you mentioned development 4 or RISC-V development. What did you mean with that? Yeah, the RISC-V development on, I think, one of the slides earlier or something. Do you know what I mean? Yes, this one.
Yes, so okay, so I think I would say JSC is involved in multiple levels. So the first level is this EPI project. Let me EPI or EUPEX, one of the two. I forget exactly which one. And here they are actually developing a RISC-V chip, or this is an ARM chip, but this is a similar project, I think. EUPEX maybe. I forgot one of them. They are actually developing an ARM chip with RISC-V accelerators, and a RISC-V chip might also be in planning. So this is a very hardware-based level. But then once you have this, when you are developing these chips, you also need to have feedback from the software developers about what kind of features should go into the chip to make it performant. And for us, I can say, at least for my lab, I can say that, for example, BLAS, the basic linear algebra routines, that would be the feedback that we can give. So all these GEM kind of operations, the matrix multiplication operations. So that is how we are specifically involved. But in general, JSC is involved at a bigger level. Does that answer your question?
Yes, thank you.
Thank you. Yeah.
First of all, I love your desktop environment.
Sorry?
I love your desktop environment.
Oh, thank you.
So, how do you go about profiling your system? You showed some profiling for the GPU, but you went to great lengths about showing how complex your actual supercomputer is and how many layers of communications is going on there. And I'm wondering, if I put my program onto your system, I run it, and my performance ain't what I expect, how do I begin profiling it? How do I find my bottleneck?
So there are, let's see. I think we have some courses, but yeah. All right. So there are a lot of actually really good resources on websites as well, vendor websites as well, tutorials for profiling. But then a lot of supercomputing centers, I think, do their courses as well. And this, if I remember, you are a student as well. So for at least for academics, I would say they are free to attend. I think they are free to attend for almost everyone.
I'm thinking tooling. Is there a specific tooling for your supercomputer, or is there a generic tool?
Okay, now I understand what you mean. Sorry. So there are always vendor-specific toolings. So for NVIDIA, there will be NVIDIA Insight systems, Insight Profiler, this NVIDIA Insight systems, and then Insight Compute. For AMD, there would be ROCm ROCm something, I forgot. Yeah. This and similar systems, there is also ROCm Profiler. Apart from that, there are these POPCO tools, which are a European effort, and they are also pretty good. And there you have tools like all this. So these ones are developed by Barcelona Supercomputing Center. JSC develops these tools. RVTH has some tools, but then all these tools, these are kind of vendor independent. So you have a collection of these tools, and then you can use them. You really have to mix and match tools depending on what you want. So this is very important.
All right, thanks.
Yeah, so regarding
sorry.
Thank you. So whenever I look into GPU programming with kernels, the kernels are usually quite small. Usually it's like you say, it's just a simple calculation or something. I had a previous project where I had to actually calculate a big objective function for an optimization problem. It's not a couple of lines of instructions, it has thousands of lines because it's a complex formula. In that case I used a CPU accelerated solution, but it always curious, like how large can a kernel be? Is there any limitations? I don't mind the time per kernel, but if those problems could be accelerated.
Yeah, just a moment. Maybe if I can show you directly. Maybe here. So now let's come to two parts here. The computation by itself, the longer the computation you have, it's not that big of a problem because it will just do more computation. You just have to ensure that it's parallelizable at every point. You see here this factor registers per thread is 122 here. How many registers you need for your computation, that is, there are a lot of things, but let's say that is for a kernel size, that is kind of the biggest things that we have seen for applications. Often when they have huge kernel, they would exceed 255 registers per thread here in NVIDIA CPUs, and then they would run into a lot of memory swapping issues and the performance would kind of go down. So that is one big thing I would say. Apart from this, there is not a lot else. So As long as you can reduce the number of registers, then you are fine. Then there are other techniques sometimes. If you cannot reduce the number of registers, then no, this is not this is the presentation I wanted. Then sometimes there are other techniques where you can use groups of threads so that they can communicate faster. So there are techniques for this.
So instruction size doesn't matter. Like I can have a large program even though the number of registers I need would be small. Like would it still be possible?
Yeah, because you would be in this regime here. This regime here, because you are bound by compute. And if you have to do that much compute, you have to do that much compute. So that's fine.
Okay, so the actual code size will not be an issue then, because anyway, of course there's a lot of instructions in my kernel, but the memory I actually need will be small. The registers I'll need will be small, but just a lot of instructions. So in that case, it will be fine, I guess.
Yeah, because even if you have a lot of instructions, if all of them are the same, then all of them fit in the L0 instruction case or the L1 instruction case, then you don't have to worry about that, I would say.
All right, thank you.
Thank you.
Okay. Do you have
last one, which is non-technical. So who owns this Forschungszentrum Jülich? Is it a public institution? Is it a private institution?
The real answer that I can give is I don't know, because I've never looked into it that well.
Oh.
Because it is funded from the government, right? It is a part of Helmholtz Institute.
I tried to check on Wikipedia and on the page.
Thank you. 60% the federal government and 40% state of Andorra.
What is the remaining? 60% is government and
60% federal and 30% state government of NRW. I didn't know that. Thank you.
So then I also have a question. So you were talking about operations per byte, right? But your example was working on floats. So was it actually only a quarter operations per byte? Or when you say byte, do you mean floats?
No. It would be quarter operation there. Yeah.
Thanks. All right then. I think this is the most questions we ever had, that I can remember at least. So big thank you to Jayesh.
Thank you.